We left off last time. We had drawn this velocity time graph for the car, speeding up, staying the same speed, and slowing down. Now I'd like to make this into a position time graph. So we want to know at what position we're at any given point. I'm going to make myself a little bit of room over here. If you remember previously, our distances were what our areas were. So if I want to make this position time, I started at 0, 0. The area of my first increment, this triangle here, was 100 meters. That took 10 seconds. So at 10 seconds, I'm at 100 meters. The next distance I traveled was this rectangle in the middle. That was 20 meters per second for 20 seconds. That was 400. I have to add 400 to 100. That gives me 500. This took an additional 20 seconds. This took me to 30 seconds. Then finally, I slowed down for the last 30 seconds. So it'll take me to 60 seconds. And I traveled this area, which ended up being 300. So now I'm at 800 meters. So I need to graph those 3 points. All right, my biggest value on the y-axis, make this a little bit smaller, is going to be 800. On the x-axis, it's going to be 60. So again, I'm going to take 800 and I'm going to divide by how many increments I have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 1, 2, 3, 4, 5, 6. So I have 800 divided by 26. I cannot do that in my head. I got 30.7. I'm going to round up to a convenient number. I say a convenient number is 50. So now if this is 0, this would be 100, 200, 300, 400, 500, 600, 700, 800. So I didn't make it all the way to the top, but I'm using that much of the graph. So it's more than half. And I'm going to be able to make out better on the x-axis when I count these up, because this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4, 5, 6, 7, 8, 9, 30. And so when I take 60 divided by 30, I get 2. That's a pretty good division. So it's going to be 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. And then the last one's 60. Because that's what our... All right, and I'm going to put my ordered pairs down. So I started at 0, 0. We go back to the previous slide. We'll see that in the first 10 seconds, we got to 100. So I'm going to have 10, 100. Then, for 20 seconds, I stayed at the same speed and went an additional 400 meters. So now I have 30, 500. So I have 10, 100. I'm going to have 30, 500. And then we end up at 800 at 60. So I'm going to have 60, 800. So how do I connect these? What should it look like? On a distance time graph, if it's constant velocity, it's a straight line. Do we have constant velocity for any of these segments? We did, the middle one. So this should be straight. The other two have acceleration, so they should be curved. I need to know whether it should get steeper. Is the velocity increasing? Or less steep? Is the velocity decreasing? For the first 10 seconds, I go from 0 to 20 meters per second, so it should be getting steeper. So this one should be curved. It's going to start off with the slope that's 0 at 0, so it should almost be a horizontal line that curves up to there. It should seamlessly transition between those points. So at 9.9 seconds, I should have almost the same slope that I have at 10 seconds. On the other end, I slow down for the last 30 seconds. So this should have this and curve down like that. And this slope should end up being 0 at the end. So these two show the same thing. I get the same information from this graph and from that graph, even though they look much different. I included the work for the previous one we saw for the accelerations. All right, so comparing these. When an object's at rest, when it's speeding up, when it's slowing down, when it's going forward and backward. So here we have something moving forward at a constant speed. Its slope would give you the speed. To graph this would just be a horizontal line. The acceleration would be the slope of this line, which is 0. Something going backwards, it's going to have a negative slope. It still isn't changing. It's still the same velocity, and it's a horizontal line here. Again, our acceleration is 0 because the slope is 0. Something that's speeding up, on the position time graph, it's going to have a steeper and steeper line. If it's constant acceleration on the velocity time graph, it would just be a straight line. The slope of that line would give you the acceleration. So if I want to go from velocity to position time, I know that from here to here, I'll make that just like T1, the velocity is increasing. That tells me I have acceleration. That tells me this should be a curve. So from 0 to T1, I should have a curved line. From T1 on, I have constant velocity. What does that look like on a position time graph? That's going to look like a line that goes straight. In the second one, I have a velocity that is decreasing down to 0. So that means from here down to there, it should be getting less and less steep. At this point, which again I'll call T1, the velocity is 0. This object has momentarily come to rest, change directions. So on this graph, it's going to start with a steep slope that's positive and end up at 0. Slope at T1. Then it starts speeding up in the negative direction as it goes down. So this should start curving back down. So what can I tell from a velocity time graph? The slope is going to be the acceleration. The area is going to be the distance or displacement. What can I tell from a position time graph? My slope is going to be my speed or my velocity, and a curved line means we have acceleration. This is not necessarily constant acceleration, but we're going to deal with mostly constant accelerations. All right.